Before the turn of the millennium, before the concept of instantaneous digital access was normalized, the computational landscape was defined by SDRAM, synchronous dynamic random access memory. The name sounds impressive, but the reality was often excruciating. The source memory was so fundamentally slow that the simple act of launching a new application, of clicking an icon, and waiting for the gears to turn, felt akin to the agonizing ritual of waiting for a dial-up modem to connect. It was the digital equivalent of a full creaking stop every time the CPU needed to grab a new set of instructions. Then, the world changed with one simple acronym: JITTR1. It launched in the year 2000, and it wasn't just an upgrade. It was a conceptual re-engineering of the memory pathway. DDR stood for double data rate, and the meaning was both simple and profound. It meant the memory could transfer data twice per clock cycle instead of the restrictive, one-at-a-time rate of its predecessor. Imagine a single-lane highway. That was SDRAM. Every car, every piece of data, had to wait for the car in front to fully exit before the next one could proceed. DDR1, on the other hand, was like instantly upgrading that road to a two-lane highway, where data could be transferred on both the rising and falling edge of the clock signal. Suddenly, the traffic jam dissolved. Suddenly, your PC didn't crawl at a glacial pace. For the first time in a meaningful way, it walked. This was the very foundation of the modern computing experience we take for granted today. In that era, the specifications were staggering, purely because the baseline was so low. Owning a machine with 256 megabytes of RAM didn't just mean your PC was functional. It meant your PC was a genuine beast. It represented an enormous investment and a significant performance ceiling that felt limitless. Compare that to today, where the average smartphone we carry in our pocket often comes equipped with 8 gigabytes. The scale of the leap is almost dizzying. Physically, the JITTR1 modules were distinct artifacts of their time. They operated at a relatively high voltage of about 2.5 volts, which was necessary to ensure signal integrity at those groundbreaking speeds. Desktop modules utilized 184 pins, while their laptop counterparts, designed for tighter spaces, used around 200. And you could spot one instantly. The stick had a single, clear notch positioned right in the center of the module. This notch was the physical indicator, the design cue that said, "This is the double data rate generation." Speeds, measured by today's standards, were modest, ranging from an effective 200 MHz up to 400 MHz. Yet, this translated to a crucial bandwidth increase, topping out around 3.2 gigabytes per second, a monumental throughput for the time, enabling the rise of demanding systems built around the early Intel Pentium 4 and the powerful AMD Athlon processors. Each individual stick typically maxed out at 1 gigabyte of capacity, a generous size back then, and it achieved its speed through a mechanism known as a 2N prefetch buffer. Let's break down that 2N prefetch because it's a critical piece of the puzzle. If DDR itself meant transferring data twice per clock cycle, the 2N prefetch meant the memory controller could actually grab 2 chunks of data per clock cycle and prepare them for transmission. It wasn't just a bigger pipe. It was a system that could anticipate and stage the data, ensuring the pipe was never empty. This smart anticipation is what gave the systems of 2000 to 2003 their perceived snap and responsiveness. The downsides, of course, were the compromises inherent in pioneering technology. That high 2.5-volt operation meant a significantly higher power draw and, consequently, a lot of heat. As the text notes, your RAM could literally double as a hand warmer. Capacity was also limited by today's metrics, topping out at 1 gigabyte per module. But if you were one of the architects who built a PC around 2001, you'll remember a different reality. Your RAM was often louder than your case fans, thanks to the cooling required, and it was certainly costlier. A single gigabyte of this cutting-edge JITTR1 could easily command a price of $100 back then. Think about that for a moment. $100 for 1 gigabyte. Today, for the very same $100, you can purchase a 16 gigabytes kit of DDR for a 16-fold increase in capacity for the same investment. This initial leap, with all its heat and cost, set the stage for everything that followed. The march of technology, particularly in the realm of computing, is characterized by a relentless drive for efficiency. Thus, in 2003, we were introduced to the next evolution, DDR2. The marketing promise was irresistible. Twice the speed, half the power. It sounded quite literally perfect. It seemed like the natural, inevitable successor to the hot, High voltage Jitter 1. But here's where the story of memory becomes genuinely weird and deeply instructional. The truth is, Jitter 2 was indeed faster on paper. It had a higher internal clock rate and much greater bandwidth potential. Yet, in real-world, daily use, there were frustrating scenarios where the supposedly superior Jitter 2 was actually perceived as slower than its predecessor. The culprit? A phenomenon known as higher latency. This is one of the most important concepts to understand, not just in computing, but in life. Latency, in the context of memory, is the time delay between the moment the CPU asks for a piece of data and the moment the memory module actually starts to deliver it. Think of it as the startup time. DDR2, in its quest for maximum throughput, had a longer startup time than Jitter 1. Let's expand on the magnificent analogy provided. Jitter 1 was a small truck that started moving instantly. It was nimble, quick off the mark, and perfect for zipping small packages, quick application launches, single instructions across town. It didn't have huge capacity, but its response time, its latency was phenomenal. DDR2, however, was a bigger truck that took longer to get going. It had a much larger engine and more payload capacity, higher potential bandwidth, but it required a brief measurable moment of winding up before it could start its delivery run. For the quick, bursty tasks that defined early 2000s computing, opening a menu, launching a spreadsheet, Jitter 1's instant responsiveness sometimes won the race. The lag in waiting for the larger DDR2 truck to start moving outweighed the benefit of its ultimate speed. But here rests the crucial pivot. When you started throwing truly heavy workloads at the system, large video files, multi-gigabyte games, or running multiple applications simultaneously, DDR2 crushed it. Its higher throughput meant that once the truck was moving, it moved exponentially more data per second. It was the necessary step toward true multitasking. Physically, the efficiency improvements were significant. Why this seemingly small, almost pedantic shift? It was a stroke of genius in industrial design. It was intentional, a physical failsafe. It was implemented specifically so that a hurried, perhaps frustrated PC builder couldn't accidentally try to force a DDR2 stick into a DDR1 slot. A small difference in pin alignment or voltage could instantly and completely fry your motherboard. The system engineers knew that in the heat of a PC build, people would always try the close enough approach. The shifted notch was their elegant solution to ensure physical incompatibility prevented electrical catastrophe. It's a fantastic lesson in designing systems to preempt human error. Clock speeds dramatically expanded the potential of the platform, doubling from 400 MHz all the way up to an effective 1066 MHz. Despite the initial latency hang-ups, the long-term benefits were clear. Efficiency was vastly improved, heat output dropped significantly from the hand-warmer levels of Jitter 1. And capacities expanded, allowing single sticks to finally hit a monumental 4 GB, a mind-boggling amount by mid-2000s standards. While DDR2 is now a technological fossil, it remains a fascinating case study, an upgrade that was faster on paper but required a shift in perspective and heavy workloads to truly appreciate. Have you ever bought a new tool or device that was technically superior, but you preferred the old, simpler version because its startup time was faster? It's the same DDR2 paradox applied to our daily choices. If Jitter 1 was the genesis of speed and DDR2 was the awkward adolescence, then DDR3, which arrived on the scene in 2007, was the mature defining standard. This wasn't just another generational upgrade. This was the memory that powered and defined an entire decade of gaming PCs and the emergent content creation boom. This was the foundational era of the digital landscape that brought us Minecraft, Skyrim, and the global phenomenon of League of Legends. If you built a gaming machine anytime between 2008 and 2015, the chances are overwhelming that you relied on Jitter 3 and you experienced its transformative power. Boot times, once measured in minutes, dropped to mere seconds. Games loaded not with the frustrating, perpetual "please wait" screen, but with an actual expectation of speed. And crucially, multitasking finally worked without compromise. You could game on one monitor and stream a video guide on the other, a feat that would have choked its predecessors to death. The Jitter 3 standard continued the relentless drive for power efficiency, operating at a clean 1.5 volts, with low-power versions pushing the envelope even further down to 1.35 volts. Crucially, it maintained the 240-pin count established by DDR2, simplifying the connector design, but, and this is the continuing saga of caution, it shifted the notch again. This third, new notch position was the physical, non-negotiable barrier to stop users from forcing a DDR3 module into a DDR2 slot, ensuring that the necessary voltage and signaling differences didn't result in costly mistakes. The performance gains were astronomical. Effective speeds ranged from 800 MHz up to a staggering 2,133 MHz in its consumer peak, pushing the total bandwidth beyond 17 GB per second. This was a magnitude of speed that fundamentally changed the software ecosystem. The secret sauce behind this stability and speed was twofold. First, the prefetch buffer was doubled again. DDR3 introduced the 8N prefetch buffer. Now, the memory controller could grab 8 chunks of data per clock cycle. The analogy shifts from a 2-lane highway to an 8-lane superhighway with an intelligent staging area. This massive increase in prefetch depth is why the systems felt so responsive under continuous, heavy load. Second, it introduced new flyby signal routing. This is a subtle but critical engineering detail. In simpler terms, it improved the stability of the electrical signals traveling across the stick and the motherboard, especially at higher speeds. It reduced signal noise and interference, meaning that higher clock speeds could be maintained reliably, allowing the entire platform to stretch its legs without encountering random crashes or errors. This stability made the memory module more robust, more dependable, and a true workhorse. The Jitter 3 era is indelibly linked to some of the most legendary CPUs ever created. Intel's Core i5-2500K and the i7-3770K. These were processors so good, so far ahead of the curve, that many enthusiasts today still refuse to upgrade, holding onto these vintage setups with fierce loyalty. And for good reason, even today. A well-balanced Jitter 3 system can confidently handle 1080p gaming and basic video editing without breaking a sweat. It speaks volumes about the longevity and the foundational strength of the DDR3 platform. However, it wasn't without its quirks. DDR3 became legendary for running hot enough that the phrase, "hot enough to cook eggs," felt less like hyperbole and more like a technical warning. Managing the thermal load of high-speed Jitter 3 was a genuine concern for PC builders. The sheer value of this technology today is astonishing. A 16 GB kit of Jitter 3 can be purchased for a mere $25 to $35, making it an absolute perfect choice for ultra-budget builds, retro gaming PCs, or breathing new life into older workstations. But we must acknowledge its limits. When faced with the demands of editing 4K footage, or attempting to feed the data requirements of the latest power-hungry GPUs, DDR3 finally reveals its age and becomes the undeniable bottleneck. It will work, but the lag, the stuttering, and the frame drops will be a constant, felt presence. The story of DDR3 teaches us a powerful lesson about technological longevity. Sometimes, the sweet spot of performance and stability can define a generation. If you are still holding on to a Jitter 3 system, what is the single component that makes you refuse to upgrade? Tell us your story of loyalty and legacy. The launch of DDR4 in 2014 is a perfect case study in the unpredictable nature of market adoption. Here's the dirty secret. When it first arrived, nobody cared. DDR3 was fast enough. It was stable, it was affordable, and it was widely available. Early Jitter 4 was expensive, offered only marginal real-world speed gains, and demanded a costly switch to new motherboards and CPUs. Gamers ignored it. Reviewers often called it unnecessary, a solution looking for a problem. It languished in the technological shadows, failing to ignite the spark of consumer excitement. But then, as in any good story, a major plot twist arrived. That twist came in the form of AMD's Ryzen processor launch in 2017. The Ryzen architecture fundamentally changed the relationship between the CPU and memory. Suddenly, speed mattered not just the raw throughput, but the specific high-frequency speed of the memory. Ryzen CPUs were incredibly hungry for fast memory. The faster your Jitter 4, the better your processor's internal components communicated, and the better your overall performance. The technological landscape was instantly rearranged. DDR4 went from a meh curiosity to a genuine must-have component, driving a massive wave of adoption and innovation. This generation marked another major step down in power, operating at a super-efficient 1.2 volts. The pin count went up again, settling at 288 pins. And the explosion in clock speeds was relentless, starting at 2,133 MHz, quickly jumping to 3,200 MHz, pushing on to 3,600 MHz, and finally breaking the 4,000 MHz barrier for serious enthusiasts. This explosion in speed was accompanied by a necessary collapse in price and an expansion in capacity, with individual consumer modules capable of hitting a staggering 128 GB. By the year 2020, DDR4 was not just dominant. It was the undisputed king, and for most users, even in the current year, it retains that title. DDR4 introduced fundamental architectural improvements that made it far more than just faster. It made it smarter RAM. One major innovation was the concept of bank groups. Imagine your memory stick is a library. In older generations, when the CPU requested a book, a data chunk, the entire library had to pause while that request was processed. Bank groups divided the memory into independently accessible sections, or banks. This meant the memory could process multiple requests in parallel, allowing the CPU to access data from one bank while another was being refreshed or prepared. This parallel processing is a huge subtle reason why DDR4 systems feel so snappy under heavy loads. The second crucial addition was CRC error checking, cyclic redundancy check. This built-in stability mechanism ensures that the data being transferred is accurate and hasn't been corrupted by electrical noise or interference. This enhanced stability was vital for pushing the clock speeds so high, resulting in a more reliable and robust memory system. In the real world, DDR4 easily handles the demands of both 108OP and 144OP gaming, provides smooth and reliable video editing performance, and can even tackle light 4000 work without crippling delays. It is, quite simply, the sweet spot for the vast majority of users right now. The current pricing further solidifies its value proposition. You can find high-quality 16 GB kits for a very reasonable $40 to $60, or jump up to a massive 32 GB for just $80 to $100. It offers incredible performance per dollar. However, a core lesson of memory evolution continues to hold true. The physical and electrical divide is absolute. DDR4 and the subsequent DDR5 are not interchangeable. The notch positions, the pin layouts, and the operating voltages are all different. An upgrade in memory speed almost always demands a compatible CPU and motherboard. When performance and value align so perfectly, as they do with DDR4, how does one resist the temptation to always seek the absolute newest, most expensive technology? It's a lesson in optimization over excess. If DDR4 was the king of the current age, DDR5, which arrived in 2021, is the herald of the new era. It is memory built not just for today's tasks, but specifically for the incredible demands of tomorrow. The explosion of generative AI, the ubiquitous use of 4,000 and 8,000 content creation, and the continued push for higher frame rates in CPU-heavy games. The pursuit of efficiency continued, pushing the operating voltage down to an almost unbelievable 1.1 volts. It maintained the new standard pin count of 288 pins, but true to form, the memory industry moved the notch once again, a final, absolute preventative measure against accidental insertion. The base speeds alone are staggering, starting at an unheard of 4,800 MHz, but the high-end enthusiast kits are rapidly pushing the boundaries, now hitting 9,600 MHz and beyond, offering a potential bandwidth north of 38 GB per second, a theoretical throughput that is almost exactly double the fastest DDR4 modules. This is the memory equivalent of breaking the sound barrier. But the real genius of DDR5 lies in its core architecture, specifically the introduction of dual subchannels within each module. Think of a DDR4 memory stick as a single, large shipping lane that is 64 bits wide. Data moves one direction down that lane. DDR5, however, takes that same 64-bit channel and effectively splits it in half, creating two independent 32-bit subchannels. Why is this revolutionary? Because it means that each module can handle multiple data streams simultaneously. This is not just faster. It is exponentially more efficient at handling the chaotic, simultaneous requests of a modern operating system running multiple background tasks, AI computations, and an open game. DDR5 also brought enterprise-level stability features to the consumer space. It includes on-die ECC, error-correcting code for real-time error correction, which dramatically increases stability under the kind of intense, continuous load necessary for rendering or compilation. Furthermore, it integrates power management ICs, PMICs directly onto the stick itself. In older generations, power management was handled by the motherboard. By moving it onto the memory module, DDR5 achieves much more precise and localized power delivery, which is essential for hitting those extreme clock speeds reliably. The capacity is equally massive, reflecting a future where data requirements are essentially boundless. Consumer sticks are already reaching 128 gigabytes, while server modules are hitting a truly incredible 512 gigabytes per single stick, more memory than most people will ever use in a lifetime. For gamers, the real-world benefits are still evolving, generally resulting in slight improvements to frame rates, primarily in titles that are heavily bound by the CPU. The true, undeniable benefits of DDR5, however, are found in the professional creative sector, in heavy video editing, 3D rendering, simulation, and high-level multitasking. These are the tasks that can fully saturate the massive bandwidth and leverage the superior latency and dual-channel efficiency. Unsurprisingly, this pioneering technology comes at a premium. Entry-level 16GB kits currently start around $80 to $120, and the high-speed specialized kits can easily cost $200 or more. The upgrade path for DDR5 is an ultimatum. It is only worth it if you are committed to a full, brand-new system build utilizing modern chipsets like Intel Alder Lake, Raptor Lake, or AMD Ryzen 7000 series and beyond. Attempting to upgrade the RAM alone is simply not possible. The platform needs to be built from the ground up for DDR5. The story of DDR5 is a peek into the near future. It teaches us that true innovation often lies in architectural efficiency, the way the data is handled rather than just sheer speed. When we see technology offer capacities that truly exceed human need, like 512 gigabytes per stick, what philosophical line do we cross? Is it a sign of readiness for the future, or simply technological over-engineering? The journey from DDR1 to DDR5 is a chronicle of constant improvement. Lower voltage, higher speeds, and geometrically increased capacity. But the complexity of this evolution has led to a handful of pervasive, persistent myths that plague new PC builders and often lead to costly mistakes. Before we wrap up, we must dismantle them, because these lessons apply far beyond silicon. Myth 1. Higher megahertz always equals better. This is perhaps the most dangerous misconception. The belief that faster RAM is always faster is a trap. Beyond a certain point, pushing for higher megahertz provides only minimal, marginal gains unless your specific CPU and demanding workload are designed to leverage it. For the average user, and crucially for the majority of gaming scenarios, latency often matters more than raw megahertz. A stick of RAM with a slightly lower clock speed but tighter, lower latency timings, for example, CL30 instead of CL40, will often outperform the higher megahertz counterpart because it can start delivering data faster. It's the speed of the start, not just the speed of the run. Myth 2. You can mix different RAM speeds technically. You can slot different speeds of RAM into the same motherboard and the system might boot. But this is the digital equivalent of self-sabotage. Every single stick in the machine, even the fastest one, will be forced to run at the speed of the slowest stick installed. The computer, for the sake of synchronization, can only operate as fast as its weakest link. It truly is like trying to run a relay race with one person wearing track spikes and another wearing flip-flops. The team's time will always be dictated by the slowest runner. Consistency and uniformity are paramount to memory performance. Myth 3. RGB makes it faster. This is the fun one. Nope. The addition of vibrant, customizable RGB lighting on a RAM stick only serves to make it prettier. You will get 0 extra frames per second (FPS) from the aesthetic lighting, though you will achieve a glorious 100% more glow and appeal. While it's certainly attractive, remember that performance is purely in the specs, not the luminescence. Myth 4. DDR4 works on DDR5 boards, or vice versa. An absolute and final no. As we've detailed through the shifting notches, the changing pin counts, and the differing voltages, these generations are fundamentally electrically incompatible. Attempting this is the fastest way to risk permanently damaging your components. Always, without exception, consult your motherboard specifications before purchasing memory. Myth 5. More RAM equals always better. This is the great temptation of the consumer. It's a pursuit of excess. While more RAM is certainly better up to a point, there is a clear performance ceiling for various tasks. For dedicated gaming, 16 GB is the widely accepted ideal sweet spot. For heavy creative work, complex video editing, 3D rendering, or large-scale virtual machines, 32 GB provides the necessary buffer. Anything significantly beyond that, 64 GB, 128 GB, is primarily reserved for server workloads, specialized scientific tasks, or frankly bragging rights. Spending an extra $100 on RAM, you never uses money better spent on a faster CPU or GPU. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.